So what's the difference between analog and digital? Nobody here knows? Nobody knows the difference between analog and digital? And we covered that back in PLC 1. If you don't know how to define it, what would be some examples? What would be examples of digital? So what we've dealt with so far is nothing but digital. It's either what? It's either on or off, true or false, right? You understand? The problem is that we don't live in an analog world, or we don't live in a digital world. We live in an analog world, which means things vary, constantly vary. An example would be today's temperature. So what was the high today? What was it supposed to be? I think it was around 50. And what was the low? And did it jump from 28 to whatever was the high today? What did it do? But slowly varied. So basically, analog gives us the ability to deal with infinity. So basically, an analog signal varies between 2 points in an infinite number of combinations. Like we say, we have 24 hours in a day. Is that analog or digital? It's analog. Then we subdivide that down into what? Minutes. And we subdivide that down into seconds. And then we got milliseconds. We could have microseconds. We could have nanoseconds. We have picoseconds. Why? Y'all understand? So time varies infinitely between each minute. There's an infinite number of combinations between each minute. So the problem is that of course computers can't deal with infinity. They have a fixed number of bits that they can deal with. So what we do is we understand digital. We have single bit digital analog devices or digital. So we have. Let me go back. We have devices called analog to digital converters. Okay, I think that would be better. Right? I keep forgetting where it's at. So what does an analog to digital converter do? Gilbert, what does it do? But it's how does it do it? So we've got what we call a single bit analog to digital converter. So that means these guys have a threshold. So even what they're sensing varies between an infinite number of combinations. Once it hits a threshold, the A to D converter would turn on. And then when it drops below a threshold, the A to D converter would do what? Would turn off. And this is what a lot of our sensors are. A lot of our sensors have A to D converters built into them. So even though they sense an analog quantity, they have an A to D converter built into them. So if you take the sensors class, we have a temperature sensor, we have a pressure sensor, and pressure is analog, right? You understand that? But we have a single bit A to D converter in there that we can have. If I'm going to represent an analog value though with an A to D converter, then we're going to have to represent it with a certain number of bits. So the number of bits that you in your A to D converter, what this does is this sets the resolution of the A to D converter. Because we can't represent infinity, right? Y'all understand? So this guy here's got true analog input. So these have A to D converters built into them. And here's the two. How can I represent infinity? So, okay, so with 16 bits, I can represent 65,536 numbers, right? With 32 bit, with infinity, I would have to have an infinite number of bits. So computers can't deal with infinity. So what we do is we say, okay, when I say I got a 64-bit microprocessor, then by George, you can represent 2 to the 64th combinations, right? You understand? No more. You can represent less, but that's the maximum you could do. And that's what we're setting them right now. We're setting here with 64-bit processors, right? So digital is going to have a certain resolution to a certain number of bits. Okay. And of course, the more complex the A to D converter is, so the way the multi-bit A to D converters, we would bring. Sorry, get out of this. So the multi-bit A to D converters. I didn't mean to do that. So the multi-bit A to D converters, we would bring it in. Okay. And we'd bring an analog input, and then over here we would get a certain number of binary bits that would represent the analog input. And the more bits we have over here, the better the resolution, the more accurately it would be able to represent the binary number. That makes sense? And we would compare it to something. So our input on the 1100 can vary from 0 to 10 volts. So at 10 volts, all these bits would be set to 1. At 0 volts, all of them would be set to 0, and anything between that would give us a close representation depending on the number of bits. Does that make sense? So this guy's got a 10-bit A to D converter in it. So we'd raise 2 to the 10th. Anybody know what 2 to the 10th is? I got y'all's chart, right? Oh, y'all still don't have that, right? It'd be 1,024. But 0 is one of those things, so I could get 1,023 different combinations out of that. That makes sense? Yes or no? So what I would do, I say, well, I'm going to take this binary number over here. Is going to take this 10 volts and split it into 1,023 different numbers, and each number represents a certain analog input. So the way we would calculate the resolution, my output is this, right? Sorry. My input is this, my output is that. So we'd come over here and we'd take 10 and we'd divide it by 1,023, and that would give me my resolution. I can do that over here. I got my calculator. Let me bring my calculator up. Now it can't be 9.77. 1,023. So it can't be 9. It might be milli or something like that, but it can't be 9.77. Yeah. So this would be what we refer to as the transfer function. So once I understand that, once I know what each step counts, then I can make it mean something, right? You understand? So of course, so here's the A to D converter input on the MicroLogic. Load this up. So here's analog, and we got 2 channels. We got channel 1 and channel 2, and then we got a common for both channels. That makes sense? This is what we call, if we read the manual. No, that's not what I want. So anytime you hear the term single-ended, it means we use 2 conductors to send the signal. One of them we consider the signal conductor, and the other one we consider to be the common. And it could be grounded. And this is referred to as single-ended. The problem with single-ended is it's really susceptible to electromagnetic interference, which means if we got a magnetic wave that moves through this, it's going to induce a voltage into this wire, but since this is usually referenced to common, it's not going to induce it into that. That gives us problems. So they came out with another interface that's really popular now. It's called differential, where we don't ever use common as one of our signals. We have what they call a non-inverted. They signal that with a plus. And then we have an inverted. They call that a minus. So the signals that I'm sending, the analog signals I'm sending, would come over here, and all this would be, if I can draw this right, would be a mirror image of the other one. So we always have a difference in potential, but we never reference the two signals to ground. And this is called a differential. Now, differential works on the technique where we have what we call a differential amplifier that only amplifies signals moving in opposite directions. So if we have a magnetic wave that passes through this, it'll put a pulse in this one, and it'll put a pulse in that one, but these guys, it'll put a pulse in that one, but these are moving in the same direction. So the differential amplifier will reject this. This is what Ethernet uses, wired Ethernet uses. This is what USB uses. So if you ever looked at the signal or the wiring of the USB cable, it's going to say plus and minus power, and then it's going to say plus and minus signals because it uses differential. So USB, we could send that thing about 50 feet and not worry about noise because it uses differential signal. So this guy would pick up a lot of noise. So we have to which I hadn't figured out how to do. So they have analog filtering, and I hadn't figured out how to do that yet, but I can't figure out where to set it. I understand it, but I can't figure out where. This right here doesn't tell you where to set so it says I can open my controller, go to I/O configuration, go to slot 0, selected the embedded configuration, but when I do that, it don't do anything. So it says I can go to I/O configuration and select this. Then it should have the filtering in here, but here's filtering, but undoubtedly I have to be offline to do it. Yeah, so here's the filtering right here. So undoubtedly I have to be offline to set the filtering. Did I close out the menu? Okay. It says it uses input words what? 4 and 5. And then channel 0 would come in on word 4. And then channel 1 would come in on word what? 5. So our two integrated inputs are 0 right for inputs. This would be out in 4. So it would be I4. So when you look at my program, so you don't have an instruction for it, it's just there. So if you wanted to access the analog inputs, all you have to do is analog word 4. So here I'm taking input 4 and I'm accessing the analog input. And then what I have connected to it is I have a potentiometer. What can we do with a potentiometer? Oh, y'all have had intro, right? What do we use a potentiometer for? Yeah, to adjust the voltage. So here's my potentiometer. Okay, I've got it hooked up. Here's my 2 power leads coming into my potentiometer. So this will be common. So all I do is run my common up to the common for my input. Huh? This thing won't focus in. Sorry. Oh, that looks pretty good. Okay. So this is common. So this is running. So I'm using the power supply off the trainer, and then I'm running it through a circuit that cuts the 24 volts down to 10 volts for the pot. So even though I'm powering it up off 24 volts, I cut it down to 10 volts for the pot using a resistor. It's really amazing. So this goes to my power source, and this is my signal source right here. So my power comes in to my pot. This is where I get the power. This is, so this will go to one side of the pot. This will go to the other side of the pot. And then this would be my signal source. And what I have to do is I have to run my common up to the black lead right here of my analog input. But this would be any analog sensor, right? You understand that, like a temperature sensor or a pressure sensor or something like that gives me an analog output. All we have to do is that analog output would have to be, for this one, it would have to be in voltage, 0 to 10 volts, right? 0 for minimum and what? 10 for maximum. So when I come up here now and look at that input word, what I should do is when I turn the pot, what do you see my input word doing? That's changing. So all I do to access it is I come in and I access what? I access the input word 0, right? Everybody okay? Understand that? And then what? And then I come in, and this is the actual number coming off. You can't see it. So where's the actual number? Right here. So this is the limit. This is the limit, and this is taking the place of 2 instructions. So what we can do is, this is the one that the book teaches, how to set a range where you have a greater than followed by a less than. And here you set your lower limit, here you set your upper limit. Well, since we do this so much, what they did is they added a limit instruction. So up here we put our what? Low limit. Down here we put our high limit, and then we say, where are the tests? Where are we going to get the information from? So you notice this thing should be enabled between, when my input gets between a range of 600 and 700, right? Okay. Now the problem is though, that means nothing to me. So what's 600 and 700? I mean, because it can go all the way up to what? I don't have quite 10 volts on there. It can go all the way up to 1023. But what does that mean to you? So if I've got a temperature sensor out there that gives me 10 volts at 580 degrees, what would that mean to me? I know that 1024 would equal to 1080, would equal to 580 degrees, but all these other numbers in here don't make any sense, right? Do they? So what could we do? Y'all understand what I'm saying? Yeah, so what temperature would that be? So I've got a temperature sensor that outputs 10 volts at 580 degrees. So when this thing gives me 1023, that means I've got 580 degrees out there. So what would my temperature be right now if it gave me back a count of 735? What we would do is we would just take that and convert that into a temperature. We call it a transfer function. So I know I've got 1023 counts, right? So I say, okay, below is an example of a multiply instruction that would convert an analog temperature sensor that has an output of 10 volts that equals 580 degrees Fahrenheit into the actual temperature. An analog value, if an analog value of 10, would equal a count of what? 1023. So all I did was took my output, which is in degrees, my input, which is in binary, and I divided them out. You know, see that? So I say 580 divided by 1024, and it came up and gave me this binary number right here. So what I've done in my multiply command is down here in my multiply command, I've taken my input now and I'm multiplying it times my what? Times this transfer function. So now it's saying This is the temperature. Right? So this is the count I'm getting in, but this would represent 417 degrees. So this is what you would have to do, right? You understand, if you wanted to use the information that I understand degrees, I don't understand what 1024 is, right? I would like it to be converted over to some unit that I understand. So what we do is we just figure out a transfer function. So whatever I'm getting, I would take 10 volts, what? 10 volts, I'm sorry. So 10 volts would represent whatever this was, right? So let's say it represented 1,000 pounds of pressure. Well, I'd take 1,000 and divide it by what? 1,023, and then I could multiply that by that number, and now it would actually display the what? The actual pressure. And we call it a transfer function. So it's what? It's out, what I want out, and what I'm putting in, right? You understand that? So on this PLC, this right here would always be 1,023. So this is a 10-bit DAC. The 1200 over there has a 14-bit DAC on it. So that sucker has a lot better resolution, right? 2 to the 14th minus 1 would be the maximum count. So what we have to understand on A to D, we're going to get a binary number that represents an analog quantity. The more bits you use in the binary number, the better the resolution. Resolution is a term we use for accuracy. The more accurate it is. So that means this guy here is going to jump about every 10 millivolts. It's going to go to another count, right? If it's between that 10 millivolts, it's depending on what the count is going to do. Everybody okay? That makes sense? So the Siemens, I'll try to play around with that a little bit. The 1200 we have also has an analog output on it. This don't have an analog. This has an analog input. But it does basically the same thing. It's going to take an analog input and convert it over to a binary number that gives you a rough representation. It's not going to be perfect. The more bits you have on your A to D converter, the better the resolution, right? Does that make sense? Yeah. So how would you do this? You would take what? What you want out. So this would be the maximum temperature I'm expecting to measure. So 10 volts would equal that. And then I divide it by the number of bits, that's the number of binary combinations available. And then this will give us what we call this is not accurate too. I mean, you're going to have to round this somewhere. Has anybody done that? Take 580 and divide it by 1,023. It's a long number. And of course, I'm using a floating point number over here. I believe I could use an integer and it would round it for us and it would be a little more accurate.
566.9.
No, it's 96 and it keeps going, doesn't it?
566.95.
Yeah, so we have to round it sooner or later. So the more digits you carry this out to, the better this will be too, right? Understand that. The more digits you carry your conversion over. So I just wanted to give you a brief look at this because this is advanced PLCs, and sooner or later you're going to run into an analog system out there, right? We have speed sensors that are analog speed sensors. We have temperatures. If you got a furnace or something that's in your environment, you're going to have temperature sensors out there, right? You understand that. You're going to bring that into a PLC. Now you'll be able to understand it just a little bit. So any questions on what we went over last class? So going into lab and getting in there and in lab and calling me back here and say, I don't understand any of this. That's not good. So in here, there might be, most of the class in here might have the same question that you have about the last in, first out, about the stack, about S24, right? You understand that, about some pretty complicated stuff that we went over last class. So if you got any questions about that, now's the time to ask. So everybody understands that 100%. So we talked about what? We talked about the move instruction, we talked about the copy instruction, we talked about the fill instruction, we talked about the last in, first out stack, we talked about the forced out, the last in, first out, we talked about the first in, first out, right? We talked about the mass move, right? Which is and on the next test, we didn't put it on this one, but all those ands and ors and nots and nors and nans are going to be on there. So there's going to be questions on there, guys, that would say what would be the results. Of course, and I'm going to give this to you in hexadecimal. I'm going to say what would be the results if I took a number like 369A and I and it with 5496. What would my results be? And these are both base 16s. Can y'all do that? Right? Y'all shouldn't have any problem doing that. So this is the way the questions are written on the test. As far as your ands and your ors and your nots. Well, nots is pretty easy because nots you just take it and invert it, right? But you can't, you have to do it in binary. You can't and it with hexadecimal.
And isn't the problem when you write it out in binary?
You have to write it out in binary.
Yeah.
And if it's an and, you'd come up here and you'd say 3, 6, 9, A. And then you'd come down and do 5, right? 4, 9, 6. And then you'd come down and you'd say, what's 0 and with a 0? What's 1 and with a 1? So we come down here now and do this, right? So my answer would be what? Let me split them up. I lost my split. 149A. So that would be the answer to that. Can y'all do that? We would do the same thing with an OR. We do the same thing with an exclusive OR. We'll do the same thing with an exclusive NOR, right? Y'all can do that.
That deal going up on Friday.
What's that?
I wasn't doing my name. The deal on Friday.
Yeah, they won't be up to Friday.
The deal for this already up. You did it 4 weeks ago.
Not for, oh, yeah, so this one should already be up.
Yeah,
Wow.
I have
The
that.
and.
Yeah.
Yeah, but while we cover that, yeah. So y'all think y'all gonna be able to do that okay? Well, that's, no, I know that's on the next test. And I can't remember about the stack. I can't remember the questions on there about the stack, but it should be on the review. So if you got any questions about the stack pointer, about indexed addressing, yeah, but we've used 3 addressing modes. There's actually 4, but we're not going to deal with the other one. We have immediate addressing. We have direct addressing. We have indexed addressing. And then we have indirect addressing. Of course, immediate addressing. How do you identify immediate addressing? It's the operand. So it's the operand. It's a number. So the number is part of the instruction. It is the actual operand. And how do you identify direct addressing? It's a data file address, yeah. How do you identify index addressing? Hashtag followed by a data file. And then an offset, right? And indirect addressing. So indirect addressing, I don't know if we won't ever use that, but this is, the data file contains the address of the operand. Here, this is the address of the data file right in the thing, where the operand's at. This data file contains the address of where the operand's at. And what is the operand? What is an operand? This is used several times in the book, guys. What's an operand? So all these points to the operand is the operand. So if you don't understand what an operand is, then basically none of these addressing modes will make any sense to you. These are the numbers, the actual numbers the instruction is operating on. Should be in which instruction. So I come up here, this, if I AND these two numbers, this would be an operand. This would be an operand. And my answer would be a what? Would be an operand. So if I add two numbers together, the two numbers are operands, right? You understand? Right? So anything that the instruction operates on would be the actual numbers that the instruction operates on is the operand. So immediate addressing, the operand is part of the instruction. And we've used that a lot, right? You understand that? So if I say move 100, so if we use a move instruction, and then my source is 100, and then my destination would be N7, right? :0, then this would be immediate addressing because that's the actual what? That's the actual operand. This would be direct addressing because it's pointing us to the address where the operand is going to be stored at, right? Understand? If I came over here and on my destination, I put hashtag N70, then this is going to be, okay, N7, it's going to be the index register plus 0, and that's going to be where the address of the operand is at. Okay, y'all understand that? And then direct addressing, it would be N70, the contents of that would be the address of the operand. So these are some ways that we can manipulate data. This is used most often for going through tables. Index addressing also is very powerful for going through tables because what the processor can do is automatically increment that index register and automatically go through words without us doing what? Without us telling it. So we use those on our bit shift lefts and our bit shift rights. We use these on our first in, first out, our stack instructions. So these will be on the test, the addressing modes for this microprocessor, or for this PLC, the Allen Bradley PLC. Now, what addressing modes that supports? These are the ones that RS Logic support, RS Logic 500 supports. The ones that actually are supported by your PLC would be in the information about the PLC, right? So the 1100 don't give us access to the index register because it always starts with 0. We don't have any instructions on the 1100 to set the index register. So, like I said, if you've got any questions about what we talked about, y'all need to go ahead and ask them now, or anything we're doing in lab. You got any questions about what we're doing in lab, you need to ask those now, right?
I don't know where my question lies. I know I had a question about it. I got one.
So what's it, what is the activity? What does it say? What's it on? What instructions does it deal with?